Here's a scenario. You're a student or a professor trying to read up on some of the classic papers in sociolinguistics that people have told you are so good. And they are so good. Everything is going smoothly as you read the introduction, the lit review, the methods, but then you get to the results and things are suddenly more confusing. What is a variable rule analysis? What are these factor weights? They look like probabilities. It even says input probability up at the top, but something doesn't seem right here. How do you make sense of this? Well, that's what this video is here to do. First and foremost, this is not an issue of not knowing enough or the right kind of statistics. In fact, you could take all the statistics courses in the world and never really learn what these things mean. That's because these are old and insidery terms to the field of sociolinguistics. But these terms have straightforward translations into contemporary statistical jargon, which is what we're going to be covering in this video. So first, for people who know a lot of statistics, I'll quickly translate these terms into conventional statistical terminology. Then for people who don't know what the statistical terminology means, I'll try to explain the rest. I can't cover all of regression and statistics in a single YouTube video, but hopefully you'll be able to take a little bit of an understanding from here and get the rest you need from a real statistics course or a textbook. So first, for people who know a bit of statistics, a variable rules analysis, often shortened to Varbrul, is a stepwise logistic regression. If the paper mentions Goldvarb, that was the software used to fit the stepwise regression. All of the predictors are sum-coded, and the parameter estimates are inverse logit transform. The intercept gets called the input probability, and the rest of their parameters are called factor weights. If you basically understood that, great. You can close the video. If you're still feeling unsure about what this all means, I'm going to try to quickly and incompletely try to cover the basics of what you need to know to read and understand these numbers. The two most important concepts to try to grasp here are the logistic transform and how contrast coding works in statistical analysis. The first thing to understand is the logistic transform. For reasons I can't fully cover here, when we do statistics with probabilities, or in this case, outcomes that are just 0 and 1, we can't just do them on the raw probabilities. Instead, we need to transform these probabilities using the logistic transform. The math of the logistic transform is easy to write out, maybe a bit more tricky to interpret. We start with the probability, here noted with P. By their nature, probabilities have a minimum value of 0 and a maximum value of 1. An event with 0 probability will never happen, and an event with a probability of 1 always will. We can convert these probabilities to odds with the formula P over 1 minus P. This is the ratio of the probability that the event will happen to the probability that it will not. For example, if you hear that an event has 1-to-1 odds, that means the probability of it happening is 50%. The lowest odds an event can have is 0, meaning it can never happen, and the highest odds an event can have is infinity, meaning it is guaranteed to happen. Finally, to get the logistic transform, we take the log of the odds. The log odds of an event can be any real number between negative infinity and infinity, and it's actually this property that we like for doing our statistics. Let's look at the math for converting three probabilities, 0.2, 0.5, and 0.8 into logits. First, we convert the probabilities into odds. The probability of 0.2 becomes the odds 0.25. The probability 0.5 becomes the odds 1, and the probability 0.8 becomes the odds 4. Then, if we take the log of the odds, we get these values in log odds, aka the logistic transform. Another cool thing is that in the logistic space, probabilities below 0.5 are negative, and probabilities above 0.5 are positive. But what are the benefits of doing a logistic transformation? Well, one reason is that small changes in proportion towards the bottom and the top of the probability scale are bigger deals than the same change in the middle. For example, if an event changes from happening 1% of the time to happening 2% of the time, that means it has doubled in its frequency. But the same percentage point difference of an event happening 51% of the time to 52% of the time is not that big a deal. So the importance of a 0.01 shift in proportions really depends on where in the proportion space we began. On the other hand, if we convert these using the logistic transform and see how big these changes are in the logit space, we can clearly see there's been a bigger shift in the first case than in the second. Okay, great, but one more question remains. How do you describe a difference between two categories in the logit space? What do we compare to what? The contrast coding we choose here defines how we make these comparisons. A lot of statistical software will default to treatment contrasts. It will choose one category as a reference level and then report how different the other categories are from that reference level. The logit value of the reference level here is called the intercept, and the difference of the other levels from that reference level is the parameter value. Another contrast coding we can use is sum contrasts. In sum contrasts, we don't choose a reference level to compare to. Instead, we take the average value across all the levels and take that as our point of comparison. The average value becomes the intercept. Then we estimate how different each level is from the overall average, and this becomes our parameter value in our regression model. In Varbrul terms, the input or input probability is this overall average across levels, and the factor weights are how different each level is from the overall average. So how does this all work in practice? Let's take a pretend example where a speech community has two ways of referring to a sandwich with cold cuts on a long roll. Sometimes they say hoagie, and sometimes they say sub. But which one they use depends on the speech style. In style A, people say hoagie 20% of the time. In style B, they say hoagie 30% of the time. And finally, in style C, they say hoagie 60% of the time. How will these numbers wind up looking in a Varbrul analysis? Well, step one is to convert these percentages into proportions. This is almost just a notational difference. You just divide by 100. Then, we convert these proportions into logits using the logistic transform. Since we're using sum coding, we estimate the intercept by taking the average of these three values. This is the overall average rate at which people say hoagie in the logit space. Then, we estimate how different each speech style is from the overall average. Nowadays, this is where we would stop. We would report this estimate and these parameter values and log odds, and maybe some p-values from the logistic regression, and that's it. That's the paper. However, the Varbrul software did one more step and applied the inverse logistic transform to these values. So the inverse logit of the intercept is now the input probability, and the inverse logit of these parameter values are now called the factor weights. Now, the point of this video is to translate what these factor weights and Varbrul analyses are for a contemporary readership. Without an explainer of some sort, the results of these older papers are going to get more and more confusing to read. This is not a how-to, and in fact, I don't think you should do your analysis this way. Like I said, nowadays, we wouldn't do an inverse logistic transform on parameter estimates like that. And in fact, we can do more complex and interesting modeling with categorical data like this. If you're just getting started in quantitative analysis and linguistics, I would recommend using some of these search terms to look into more contemporary analysis methods. Or if you're trying to pick up a book to read about statistical analysis and linguistics, Analyzing Linguistic Data by Harold Byen is a classic, and the more recent Statistics for Linguists by Bodo Winter is also highly praised. But in the meantime, you're now better prepared to read and understand those classic sociolinguistic papers just a little bit better. Have fun.